Yeah, thank you very much. So, yeah, my name is Max Coenen. I'm from the Leibniz University in Hannover, and I'm going to present our work on Granulometry Transformer, an image-based approach for the prediction of particle size distributions of concrete aggregate. So I assume that we are probably all aware of the challenges that are currently faced by the concrete industry. For example, every 10th ton of CO2 approximately is originated from the concrete production. And furthermore, also 40% of natural resource consumption also falls into the concrete industry, while at the same time, a large percentage of waste volume is also caused by construction waste. So one way to overcome or to encounter these challenges is the usage of recycling concrete. So if we have a look on the composition of concrete, we can see that a large amount of the composition consists of aggregates, which can, at least in parts, be substituted by demolition material. However, in comparison to natural material, recycling aggregates underlie large fluctuations, which can have, if they remain unconsidered during production, which can have negative effects on the concrete's quality. So the current practice to account for the grading curve is to take a random sample, usually a few kilograms of concrete aggregate, and determine the grading curve by manual sieving and assume this curve as representative for a whole range, like a few tons of material. However, if the material underlies fluctuations, this assumption does not hold true. So what we propose in this work is to install cameras on top of the conveyor belt transporting the aggregates into the concrete mixer and find a way, an algorithm to determine the grading curve of the actual material used for concrete production. And if this information is available in real time during production, it can actually be used to adapt the mix design, to adapt the water demand or superplasticizer in real time to make sure that the desired concrete properties are reached. And this endeavor is part of a larger research project called Recycle Control. Just for interest, I put the website of this project here. So more formally, given an image or multiple images, the goal of this work is to find a mapping function which is able to derive the grading curve of the concrete aggregate that is shown in the image. And in our case, the grading curve is represented as histogram, where the percentiles defining the histogram underlie the constraint that they have to sum up to 1. So in total, this leads to a constrained multi-regression problem. And in order to define F in this work, we try to use vision transformers. So the classical way in which vision transformers work is that they divide an input image into several patches, linear project them, and with this receive the patch tokens for each patch. And for classification or regression problems, usually a learnable class embedding is prepended to the sequence of tokens, and then the whole sequence is fed through the transformer encoder, and the final prediction is then based on the final token embedding of the learnable class token, which means that all the embedding information of the actual patch tokens are neglected, although they potentially can contain rich and valuable information. So if you transfer this proceeding on our problem, we can see that the actual or the local size distribution can vary from patch to patch. So what we propose here is to decompose the overall problem of predicting the grading curve for the whole image into smaller sub-problems by letting the network predict an implicit grain size distribution for each patch, and to derive the overall distribution just as an average of the patch-wise distributions. And we argue that in this way we relax the demand for global reasoning for the network, and thus reducing the complexity for the learning procedure of the network. Yeah, if we transfer this to the architectural design, we can see that the learnable class embedding or class token is discarded here, and we derive a feature embedding for each and every patch token, which are then fed into a dense multi-layer perceptron head, and the implicit patchwise grading curves are determined, and we impose the loss on the final grading curve, which is computed as the average of the implicit distributions. Yeah, to test this whole procedure, we acquired two data sets that we made actually publicly available under the link above. The one data set consists of coarse aggregate from 0 to 32 millimeters. We synthetically created, in this case, 35 grading curves where we precisely know the grain size distribution and acquired approximately 2,000 images. And the same procedure we did for a data set consisting of fine aggregate, in this case 0 to 2 millimeters. For test settings, we used the standard vision transformers in the original paper as backbone architecture. For training, we used geometrical and radiometric augmentations during training, and we compare our results to the state-of-the-art methods as the standard vision transformer architecture and also a CNN based architecture. Yeah, for evaluation, we split the data sets in three parts for training, testing, and validation, respectively, and we performed a twofold cross-validation. And in this work, I'm going to present as metrics the mean absolute error for the predicted percentiles and the results for the Hellinger distance, which is a similarity measure between the reference and the predicted distributions. So to start with some qualitative results, we can see some examples of images here with the corresponding reference grading curves as the green line. And we see the average predicted curves as solid red line, and in the light red area we see the standard deviations achieved. So in total, from this qualitative results, we can see that it's actually possible to relatively precisely determine the grading curve in comparison to the reference grading curves. Quantitatively, we see here the mean absolute errors achieved for the different percentiles. So in the bottom row, we see the results obtained by our approach, which all lie underneath 2% of mean absolute error, with an average error of, in the last column, of 1.08, which is on par with a CNN-based architecture, with a CNN-based counterpart, and more importantly, which outperforms the standard approach of the vision transformer, which shows the benefit of our procedure of the patchwise embeddings. So these are the results on the first data set. The second data set show the same pattern, although the results are absolutely seen a little worse compared to the first data set, which might be caused by the fact that the dataset contains fine material and the problem is a little bit more complex. Yeah, and here we see the average Hellinger distance. Again, the same pattern is visible. Our proposed method outperforms the standard vision transformer, and again is on par with the CNN architecture. In the bottom graphic, we can see the cumulative histogram of the Hellinger distances, and the desired shape would be like a step curve. This clearly shows the improvement, again, of our approach versus the standard procedure. Here again, for the first data set, and the same pattern is again visible also for the second data set. Yeah, to conclude, we presented a visual approach for the granulometry of concrete aggregate for an inline concrete production control. Especially, we proposed a dense patch-based prediction showing improved results over the standard procedure. And for future work, we also like to extend the whole approach not only to predict the grain size distribution, but when we work with recycled material, also the petrographic analysis of the material and apply the approach for an automatic concrete production in real practice. So with this slide, I would like to end my talk, and I'm happy to answer questions or to discuss.